questions about lab today? Okay, we'll have our first quiz on Monday. Okay, it'll be a short 10-minute quiz. Similar to problems you'll see around in the workbook or anywhere. Largely over structures, hybridization, all that stuff. The stuff before we started physical properties. How are we doing on IR? Any questions about IR? Yes.
When we're looking at IR for OH hydroxyl groups, like we did for hydroxyl groups, we were identifying the OH group. Would you give us a more modern version of IR, or would you give us like older versions where there's a larger or wider?
I'll give you something illustrated to you already. Yeah. But upstairs you need to be aware of that, and I have mentioned that, or I will mention it again. But in terms of quiz, it's what I illustrated in the handout in the video. Okay, physical properties. Physical properties. There's 4 types of IMFs are listed in order: van der Waals attractions. Basically, electrons can be polarized. Okay, temporarily polarized. Induced dipoles, yeah? Okay, quick question. Which type of electron is going to be induced more readily? Electrons that are in sigma bonds or pi bonds?
Pi bonds.
Okay, good. Yes, why?
Because they're in the higher level.
Pi bonds are not held as strongly in a bond. They're not bonding as strongly. Okay, and so we can pull information together and make informed, estimations or hypotheses, etc. All right, everything goes together. Dipole. Okay, the dashed. So the dashed down here, like in a, basically this is illustrating what?
Non-covalent interactions.
Okay, a non-covalent interaction. You guys remember NCI on TV? Yeah. What does that stand for? Non-covalent interaction. Remember that show? Okay, that's what we're illustrating here. That's how we do it here. Okay, the partial minus is interacting with partial plus. Okay, this is charge attraction. And this is stickiness, like glue. Okay, that's how these things can stick together. This is 4 different ways things can stick together. Yeah. IMF. And so that should hopefully explain why one compound here has a much lower boiling point than the other 2. The other 2 have permanent dipoles, and permanent dipoles are stronger than weak induced dipoles. The only thing that this compound over here is, the name of this compound is what? That's right, pentane. Pentane has no dipole, but it only has induced dipoles, weaker. You see that in the boiling point. Next, hydrogen bonding. Why does the alcohol have a higher boiling point than the alkyl halide or alkyl chloride?
Hydrogen bonding.
Thank you. Hydrogen bonding. Yes, there it is right there. Do we need to say any more? You guys know hydrogen bonding, or should we talk about it? Talk about it?
It's a little recap.
What?
It's a little recap.
Recap? Okay. Hydrogen bonding is just a particularly strong type of dipole-dipole interaction. Okay, it gets its own name. It's particularly strong because the atoms involved are particularly polarized. A hydrogen bond occurs between an O, N, or F specifically the lone pair on an O, N, or F, and that's called a hydrogen bond acceptor. It will H bond to, it will form a particularly strong IMF to a hydrogen that's on an O, N, or F. And these hydrogens over here have a particular good amount of partial positive because of being on a particular electronegative atom. So the H is partial positive here. And these guys are particularly electronegative, and these lone pairs here are serve as the H bond acceptor. You can get an IMF between the two. And how can we illustrate an IMF?
Sort of the dashed line.
Yeah, so it's long there, okay, but an interaction between the partial minus. Because what's the charge of electrons?
Negative.
Yeah, instead of showing a formal charge, let's just call it partial minus. It's an area of electrons, it's an area of minus. And then that H over there is an area of partial positive because it's bonded to a very electronegative, greedy. Electronegative means greedy. Very greedy oxygen, which is pulling the electrons and leaving the H partial positive. Okay, these are particularly strong. When it involves these types of atoms, it's called hydrogen bonding. Here we show a hydrogen bonding network, showing the IMFs with a non-covalent interaction illustrated with the dashed here. And if you have a container of this alcohol, all the molecules are going to be there sticking together by this IMF. The H bond acceptor, hydrogen bonding to the H bond donor. Question, can this compound here, well, it's not a question, that compound, which is the one on the top right, cannot H bond to itself. You cannot show a hydrogen bonding network of different molecules here because what does it take to hydrogen bond?
Hydrogen bonded to
There's an acceptor and a donor. What does it take to make Velcro stick together? You need a fuzzy piece, and you need the more loopy piece, and those two will stick together. Okay? If you have two loopy pieces, it ain't going to stick together. All right? You need two different things. This is hydrogen bonding question.
Would, for atoms such as oxygen and fluorine, will multiple of the electrons engage in hydrogen bonding for each atom, or would it just be one? There's more than one lone pair equivalent for oxygen since it has two lone pairs.
Both could hydrogen bond. Yeah. But it's becomes a question. Okay. It's not certain, but both can. Or what I'm saying is, will they always? That's uncertain. They can. Okay, question here. Can this ether, that's an ether, right? It's called diethyl ether. Can diethyl ether H bond to itself?
No.
If you have multiple molecules of that around, can they H bond? No. Diethyl ether, I see an H bond acceptor here. You see a donor anywhere in that molecule? Okay. So another molecule, each molecule only has acceptors. You need one molecule with an acceptor and one with a donor, right? So no, it cannot. Question, can this molecule H bond to water?
Yes.
Yes, because if it was around water, we could show water. And now, this could be an acceptor, this is a donor. Why? Because it's bonded to an oxygen. H bonded to an oxygen. And we can illustrate a NCI right there. So it can hydrogen bond to water, but not to itself. How many H bond acceptors and donors in this drug here, Effexor? How many acceptors?
3.
Why 3? Why not 5? How did you count 3? So your answer for acceptors is 5? Who said 3? Why'd you say 3?
Yes, sir. Three, the atoms, three different H1 acceptors, you know, that you have the low and the alcohol group.
There's lone pair here, lone pair here, lone pair there, lone pair there, lone pair there. Yep. Is the answer 3 or 5?
3.
Okay. Okay, lone pair interacting with an H, right? Is the answer 3 or 5? Tell me your answer there, Beckman.
I said 3.
Why 3?
Because there's only 3 of those atoms. And
Yeah, but didn't you ask earlier about 2 lone pairs? Can they both hydrogen bond?
well, I thought,
And my answer was yes. It's uncertain, but yes.
I thought when it meant by an acceptor and donor is just talking about one individual atom and not multiple pairs on that one.
Yeah, but we didn't clarify that. This question needs to be clarified. If it had said acceptor atoms, it would be 3. If it just says acceptors, it's a little bit vague. Okay? Both these lone pairs could potentially hydrogen bond. You're going to get different answers there, 3 or 5. You need to know how to discuss it. Okay? If it says atoms, I would say 3, because there's 3 different atoms there that can participate in hydrogen bonding. Yeah? But oxygen does have 2 lone pairs, and as we said earlier, both could participate in hydrogen bonding. You have to know, ask for clarification of your question. Examples down here. These are all constitutional isomers. Why does this have a higher boiling point than that? Same formula, same size, and size is important. Why? Because that is with van der Waals, size, surface area. So they're going to have very similar van der Waals. By the way, 1 through 4, you want to consider the greatest, the most influential one, the one that has the greatest effect. So let's consider hydrogen bonding before we consider van der Waals, because it's going to be more likely to give you your answer. Why does this one have a higher boiling point than that one?
Can hydrogen bond on its own?
Yes, hydrogen bonding. Let's try it again. Why does this one have a higher boiling point than this one?
Hydrogen bonding.
Okay, good. Do you see why? If you had 1,000,000 molecules of this, they could all be stuck together by hydrogen bonding. One molecule has a donor. Another molecule could be used in its acceptor. Each molecule has both, by the way. But we're talking about intermolecular, 2 different molecules. Okay? One has a donor, one has an acceptor, and they can start hugging each other. If you got a gazillion of those, all you got is acceptors around. Okay? There's no donor there for it to stick together. Same thing here. Hydrogen bonding is very important. Significant type of IMF, and that's why the boiling point is raised for those that can do hydrogen bonding. And when you're boiling, you're talking about a pure compound. When we get to solubility, we'll talk about 2 different types of compounds, a solute and a solvent. Why does water have such a higher boiling point than H2S? Yes. Can H2S hydrogen bond to itself? No, it's sulfur. Did we see a sulfur up there? No, it's chlorine or F. Largely because the dipole is not as great here and the H is not as partial positive as it is over here. And we just call that situation hydrogen bonding. This can do hydrogen bonding, that can. By the way, instead of O or S H's, how about C H's? That's methane. The boiling point is real low. Why the difference in boiling point here? Because this one at least has what? Dipole. It does have dipole. Yes, there are polar interactions. Yes, it does have partial positive, partial minus. And the partial positive of one can stick together to the partial minus of another. We call that dipole. Can this one do that? No, it has no polarity. All that has is induced polarity. It's a very small molecule, so it ain't going to have much induced polarity. And so there's not much potential for IMFs holding those molecules together. Very easy to get it to boil. I can show the same exact thing in here as here. The difference is over here, this is much greater. Greater magnitude over here. And the greater magnitude, we call it hydrogen bonding. Over here, we just simply call it dipole-dipole. Okay? Hydrogen bonding is a special type of dipole-dipole, a stronger type. Gets its own name. Why is this dialcohol, called a diol, 200 degrees higher than this one, which is just a hydrocarbon? Hydrogen bonding, okay? These molecules are going to be able to stick together. You need to be able to explain that and illustrate it. Those molecules have no... The only stickiness over here is van der Waals. Okay, you need to get that in your own language. Okay? I throw certain, just terms and language at you. It's up to you to figure it out. Get it how you like it. Comfortable with it, reading the chapter. Okay. So you can then explain it. How you feel comfortable with it. All right? DNA. This is illustrating DNA. We know the double helix is held together by what? Yes, yes. Okay. Lots of applications of hydrogen bonding. And AT base pairs tend to pair together. They like each other because you have potential for two hydrogen bondings. There's a lone pair here. And then there is, this molecule has an acceptor and a donor right here. This one over here has an acceptor and a donor. And when these molecules approach each other, it's got two hydrogen bond potentials right here that can come together. All right. The AT and the GC has actually three. Okay, so these molecules are well designed to come together and stick together. Okay, by these NCIs. That's what holds DNA together in the double helix. All right. The fourth is ionic attraction. That's number 4. This is the greatest. Even stronger than hydrogen bonding. But when you get to ionic attraction, here we're dealing with actual ions, formal ions. Not from polarity, but actual formal ions, charged species. And that's going to be the greatest attraction. Okay? For example, if you look at this alcohol going from the 78, that's ethanol. You can convert this to an anion, an ionic. O minus and have some type of plus like sodium. And this ionic has a boiling point way higher, above 500 degrees. As a consequence of that, this is a solid at room temperature. This is actually a liquid at room temperature. I don't get the melting point of that, but it's melted at room temperature. It's a liquid, but this is a solid because the melting point is also above room temperature. All right. And it's because ionics tend to have very high boiling points. It's actually very odd to boil an ionic. I mean, I don't know hardly any example. I don't know if this is estimated or... Look at sodium chloride. Can you imagine boiling it? What's the boiling point of sodium chloride? 1400 degrees. Can you even imagine sodium chloride distilling as a vapor? I can't. The IMFs are so great between these ions that they're stuck together and they do not want to go into the gaseous phase, separate from each other. So this has hydrogen bonding, yes, but this has ionic attraction, ion-ion attraction. Okay. Now we can look at some examples, but what do we need to know there? That's the greatest. Charge attraction. Greatest type of IMF. Melting point. Melting point is very similar arguments to boiling point. That is, the more IMFs, the higher the melting point. And to get something to melt, we have to overcome the IMFs. Two compounds here, they're both amides. Primary amide and tertiary amide, right? One has a melting point of 126, one much lower. Which one has the highest melting point? Well, the one with the greatest IMFs. So the question becomes, which one is going to have the greatest IMFs if you have all these molecules in the same beaker or flask? Well, we look for our 4 different types of IMFs. Do you see any? Let's look at the strongest. Do we see any ionic here? No, so that's not applicable. Neither one is ionic. What's our next strongest? Okay. Do you see any difference here between hydrogen bonding possibilities?
Yes.
Which one can hydrogen bond to itself? The first one. Can the second one hydrogen bond to itself? No, it cannot. Does everybody see why? What does it take to hydrogen bond? Acceptor and donor. Does the first one have both? Yes. Now we're talking about IMF. What does the I stand for? Intermolecular. What does that mean? Different molecules. Like an interstate goes between 2 different states. Okay? So we need another molecule up here. All right? That can be a ring, and we can have another molecule. And now we can illustrate something. Let's draw a bond off of that nitrogen. Is that okay? Now we can say maybe that we got a NCI right there between the lone pair oxygen. What are donors and acceptors? Oxygen, nitrogen are F lone pairs. Oxygen lone pair, and that can interact with what? An H that's on a ON or F. Is this H on an ON or F? There you go. There is your H bond NCI. Can you do the same? Can you show the same for the other molecules? No, you cannot. If you can, I'd like to see it, because you're not going to find an acceptor and a donor with the other molecule. Questions?
Can the nitrogen be an acceptor? Because I know like the...
Why do you ask? Obviously from the top nitrogen lone pair, yeah, but why do you ask in this case?
Because it's the lone pair is being conjugated. It's in the
You're applying other knowledge to different questions, okay? Yes, it's very important. Because the lone pair of this nitrogen is conjugated, it's in a p orbital. And maybe you know that when lone pairs are in p orbitals, they're less reactive. They're busy doing something else. And so now I understand your question. It's possible, less likely. Or are you looking for a yes or no answer?
Yeah.
Well, there's not, science is not that clean as that all the time.
But if...
I told you it's possible.
But in the...
It's less likely, did I say that? I think that's about all I can tell you.
But in the case that there wasn't a double bond between, there wasn't a carbonyl group over there, it was just a like, single bond to, let's say, another atom, like another heteroatom, the lone pair on the nitrogen, would it be an acceptor then?
Why would it not be then? I mean, that's a basic nitrogen, standard nitrogen, and standard nitrogen should be good to go.
Okay.
It was on the other page. Yeah. Yeah. standard nitrogen, I don't know why there would be a question. I do understand your original question because here we have a lone pair of a p orbital. Okay. We need to look for some more examples to maybe get at the answer. Would you like more examples? Maybe we'll see one in which an ambient nitrogen is hydrogen bonding. Then maybe we could get a reference, and then we could include that in our report or something. Yeah? So we can search the literature, or it's very commonly done. Which is which? Okay. Did we get everything there? Was there another question to answer? MS, we can. Okay. Solubility. Okay. Again, I'm taking this to read this. Okay. Your job is to go through and get everything set in your mind, ask questions. Right. Solubility, getting things to dissolve in a solvent. We're doing that in lab this week? Anybody get something dissolved yesterday? Did things dissolve easily versus no, yes and no? Some things dissolved easily, some things did not? Okay. Did some of your predictions hold true, or?
Yes.
Okay. There's an adage here. Like dissolves like. A compound with similar properties, similar types of IMFs, will dissolve in a solvent that has similar types of IMFs. Broadly speaking, a polar compound will dissolve more likely in a polar solvent. And broadly speaking, a nonpolar compound will dissolve more readily in a nonpolar solvent. That is what it means, like dissolves like. Okay? A polar compound is not going to want to dissolve in a nonpolar solvent. In general, those are opening statements. Okay? Very general statements. There's lots of variables. Okay. For example, the two amides above. Which one would you expect to be most soluble in water? The first one, yes. Why? They both can hydrogen bond to water.
More hydrogen.
You said hydrogen bonding, right? But they both can hydrogen bond to water. Can they not? They both can, yes. And I say like. We also want to look at what type of interactions can the solute have with the solvent. Because the more they can interact by IMFs, the more they're going to like each other and dissolve. Okay? They can both hydrogen bond to water, but can you clarify beyond that?
The first one can do more hydrogen bonds.
Yeah, we can look at more hydrogen bonding, because the first one I could think about maybe the oxygen hydrogen bonding with one of these H's. The H hydrogen bonding to this O. The N possibly bonding to one of these H's. And that's 3. Maybe I can come up with 4 or 5 different. But over here I have less, because over there's no H's. And the only thing that we can do, the oxygen can hydrogen bond to an H here. But what else can it do? Maybe another 1 or 2. I think it's just 1. But over here I said 3 or 4. More hydrogen bonding possibility with this compound in water than that one. That one's going to be more likely to dissolve because it has more types of stickiness possibilities. They can interact better. Which one of the two will be more soluble in hexane? How are we doing with nomenclature? Hex 6, straight hydrocarbon, saturated hydrocarbon called an alkane. Hexane. Yes, hexane is a common solvent in the lab. Okay. You used it yesterday and today. Yeah, hexane, so it's a mixture. Okay, which one would be more likely soluble in hexane? The second one, yes. More nonpolar bonds, but explain further. Why would that make it more soluble in hexane? My answer is because these are solids. And these solids, the molecules are all stuck together. Which of the two up there are the molecules stuck together more? First one, that's why it's got a higher melting point. Since it's stuck together more, that hexane is going to have to work harder to break those molecules apart. And hexane can't compete with all this hydrogen bonding because they're so different. It ain't like dissolves like. They're not alike. See, the other one over here is not stuck together as much. There's less hydrogen bonding potential. We also see that in the lower melting point. Because they're not stuck together as much, hexane can get in there and break them apart easier. Dissolve them all. So like dissolves like, how much are they stuck together already by IMFs? How much can they interact with a new solvent? Different ways of looking at it. Okay, this is what I decided I need to do here, guys. The rest I'm going to have to do by video. All right? Mainly because it's a lot of just sort of discussion. And I can try to do it here, but I end up sort of just hitting it and trying to push through, and it might not be as useful. All right? The other reason is because certain things I know we need to keep up a good pace, particularly in large group. Okay? I know things are coming down. I think the rest of this handout will be very good for video, and I can take more time and explain things, and there's a couple of handouts in the back, some examples, and I don't have to rush through it as much. I want to do that and give that a try. I want to get that video made and posted today, midday, and you watch it like this evening, tomorrow, etc. All right? Because I want to get us to acid base. That's the next handout. All right? Lots of good stuff here. But it's more of just sort of examples, and okay, and I think that's better if I want to give that a try, okay? I've not done that before. Like this Crestor with all those, that drug with an enzyme there. There's lots of issues with that page. I don't want to take 15 minutes of our valuable time here explaining the issues with it. But it's very useful. We'll do that by video, okay? Lots of useful applications. Interesting applications. Solubility. Let's look at acid-base chemistry. I'll send you an email when I get that posted. Okay? Acid base. I think we're going to want to spend more time on acid base. All right. Some warm-up questions. These are pretty straightforward, okay? Pretty straightforward, and thus very basic and very important. Some of my questions can be a little bit more kind of out in left field, a little bit thinking. These are straightforward. Next page, also very straightforward and important. Here we go. Here's a drug, tramadol. Okay, it will react with HCl to make the HCl salt. Okay, can you show the structure of the salt? I'm not going to give you time to do it right now, but is everybody confident they can do it? Yeah? All right. Come test day. That right there could be a question right there. I sense that majority of you are not able to do that right now. Okay. What is your thought process? What's the first thing you want to be thinking about here? And this is our first reaction. Acid bases are our first reactions. Okay? But it's a standard acid-base reaction. You've done acid-base reactions, you should have done plenty. All right?
The nitrogen is going to set the hydrogen from the nitric acid. Yeah.
Didn't we have, did we say something?
You're gonna take it away.
Didn't we say something
You're
about
right.
accept?
Yeah, you're gonna take it away.
Yeah, the thief is going to accept your bicycle? I recommend that's, I suggest that's not a good term. There you go. All right. What did you do in Gen Chem? Are you able to do that? I mean, if you can do that, we can sort of move ahead. I think the majority of you are going to have trouble doing that. Not sure why. The answer is you just don't have a thought process. So, okay, you got to know how to approach things or what questions to ask, and then just do it. Okay, well here we go. Very important to know the acid-base mechanism. All right? There's a gazillion different acid-base reactions. When I say acid-base, I'm talking Bronsted-Lowry acid-base. All right? Which should mean something to you. All right? Anyone you can dream up is going to operate by the same mechanism. What is a mechanism? It's how the reaction occurs. It's the electrons moving, and we use arrows to illustrate electron movement. We mentioned this before. And any Bronsted-Lowry acid-base reaction, we're going to have a basic atom, and it's going to have a lone pair, because the lone pair is the business end. It's the thing that reacts. The lone pair does what? The lone pair makes bond to the H. The H is the H plus, the acid. Okay? We show this by, I've already given these electrons, anytime you move arrow, these electrons make bond to H. That's what that arrow is meaning. Now the H is bonded to something else. Usually a very electronegative atom can be shown as Z. Alright? It's polarized, okay, because Z is electronegative, that's partial plus. Electrons are partial minus, right? It's almost like illustrating hydrogen bonding. Except it's not just going to be a non-covalent interaction, NCI. The lone pair is actually going to bond to the H and sort of take it. So it's beyond, because hydrogen bonding is a non-covalent interaction. This is beyond that, and we're going to form a covalent bond between the basic atom and the H. And these electrons are going to move on to Z as a lone pair. The result of this arrow movement, the basic atom is now bonded to the H. That's what that arrow means. Everybody with me? Where'd the lone pair go? The 2-electron lone pair is now a bonding pair. Those 2 electrons used to be a lone pair, yeah? Okay, over here. Why does the Z now have a lone pair?
Plus bond.
Well, hopefully our arrow movement showed us, because when we do a mechanism, all results have been shown by arrow movement. What does this arrow mean to you? The bonding pair moves on to the Z as what? I told you that. There it is. Everything is there. We see the movement of electrons. This is how we do it in organic chemistry. Because seeing the electrons move is what you need to be able to see. We don't just pull predictions out of the air. We actually illustrate it. Then you can understand it better. Okay? These are called curved arrows, mechanism arrows. Very important. You will be tested on using arrows. And every time you do an arrow, I recommend saying what? These electrons do this. These electrons do this. Every time you move an arrow, these electrons. Right? That'll help keep you out of trouble. What do you say when you move an arrow? Okay, one more time. Anytime you do an arrow, you've got to say these electrons, or you will be getting something wrong. This is my advice.
So for the HC, breaking the bond for the second arrow, we use the whole bond, the arrow all the way to the end of the bond, and then do it, or can you just do it?
Okay, here's our bond. You illustrate breaking the bond. How do you want to do it? It's going to move from her, both these electrons are going to move on to me. So how would you show that?
Oh,
Why did you start over there at her elbow?
yeah. Well,
Because you're going to break it from her and move it over here. Yes, I would start over there near her and push it towards me. And that's what I did. Way over here, and I pulled them away from the H, and I moved them onto the Z. Is that what you were asking?
yeah.
Yeah. So the precision of the arrow is important. You got to pay attention, yes. Because the arrow has to mean something to you. I think when I see some students, it doesn't mean anything, and so they just have an arrow here. And it's like, then you get a WDAM. What does that arrow mean? You got to know what it means. If you know what it means, then the precision will come intuitively. Okay, mechanism error 1 and 2. I think I told you that. Charges. Acid-base reaction is going to have charge. I'm not showing any charge up here in my generic reaction. It's going to be charges. You should have seen that in Gen Chem, right? Okay, particularly if it's just plus or minus. Okay. Well, I give you some little free information in the very back. Miscellaneous points to remember. Free information, okay? I'm sure one of those is going to be looking at charge. All right, so this mechanism can be used to predict the outcome of any acid-base reaction. All right? Now can we do the one over here? What else do we need to know, though? You need to know what's the acid and what's the base. What's the acid up here? Well, that was good. I'm joking because that was easy. I knew everybody was going to get the ACL is the acid up here. What's the base? The drug. Well, I would hope you would say that because one's an acid, you've got to have a base. The other's a base. But here's the big question. Which atom of the drug is the base? Because it's going to be not the whole drug, it's an individual atom with a lone pair. And the answer is nitrogen. Why do you say nitrogen?
Because that's lone pairs on it.
Okay. Because typically, hopefully you've learned this, most bases are minus, like hydroxide. The only good base that is good as a neutral atom is nitrogen typically. A neutral oxygen is typically, now this is probably in the points to remember in the back page. A neutral oxygen is typically not basic. The only neutral atom that has good basicity is nitrogen. But what if there were multiple nitrogens? Can you determine between, okay, that's where you're going to have to consider hybridization. And we'll do more points here. You got to identify the basic atom. Now, in some cases, it may be more difficult with the acid. You guys know strong acids, but what about weaker acids? What about if there's multiple acids in the same molecule? What I'm getting at, you got your mechanism, but you also have to determine what is the base and what is the acid. Which are the two that are going to be doing that mechanism? And that's what most of the handout's about. And this is intro, okay? You should have seen all this in Gen Chem. All just intro. It's in your book. You need to make sure you know all the intro stuff. For example, Ka versus pKa. We typically use pKa's to describe equilibrium. We also know that H plus really doesn't exist by itself, but it's sometimes shown like that. Okay? The H is always going to sit with some type of other atom, like with water, H3O plus. It's an acid-base mechanism. The lone pair makes bond to H. It's the same as on the mechanism page, yeah? Stronger acid will have a lower pKa, right? Okay. So examples of acids, HCl is a strong acid, pKa like -7 or something, real low. Acetic acid, a carboxylic acid. Carboxylic acids have pKa's about 4 to 5. By the way, there's a list of pKa's on the back of your workbook. Okay. Very last page, periodic table, pKa's. Carboxylic acid is considered a weak acid. What does that mean? That means it only partially ionizes if you put it in a polar solvent like water. Right? Strong acid, yeah. Okay. An alcohol has a pK of about 16, so it's not as acidic. It's actually considered a neutral. You gotta be careful with neutral here. In some cases, neutral means non-basic or non-acidic. Okay? In other cases, neutral may be non-charged. Right? So if you're going to use the term neutral, make sure you kind of clarify what you're talking about. Here I'm saying it's non-acidic. Okay? Like water. Is water acidic or basic? Largely considered neutral. Neither. Same as alcohol. By the way, pK of water is also 16. Water and alcohols are considered not acidic. Weak acid, strong acid. We're getting less acidic, neutral. Hydrocarbon. Hydrocarbon has no acidity at all. pK is greater than 40. As we go along, we will discuss and have examples and make all this more relevant. You need to start learning some pKa's. Carboxylic acid, 4 to 5, is an important one to start with. Alcohol, 16, just like water, an important one to start with. By the time you finish Organic 2, you'll know a half dozen to a dozen. All right, question?
Will a neutral compound dissolve in water?
Why do you ask? What do you mean? Sounds like you're asking, for a compound dissolved in water, it has to be acidic or basic? Is that what you're asking? And the answer would be no. Neutral compounds can dissolve in water. Sugar's a neutral compound. Some of the examples we looked at on the previous page are neutral compounds. So again, I'm not quite sure of the question. I'd like to clarify it more. Ask again with a more specific question. Would you expect an acid-base reaction to occur? No, well, hold on. HCl is a neutral compound. You gotta know I have to know what you mean by neutral, and I don't think you used it right there. HCl is a neutral compound. So, you've got to use the term correctly or be more specific. Most importantly is I got to be sure that you understand it correctly. If I just let you go on with it, then you're going to think you're right, and I'm thinking, no, I don't know that you're right. There you go. Caphor is not a charged molecule. Okay. That doesn't mean you can't do acid-base chemistry, because HCl is not a charged molecule, yet is acid-base chemistry. All right? So you have to keep asking and get it right in your mind of what's important and, okay. Degrees of acidity. What is all this based on? Based on 4 things again. Here are the most important things, 1 through 4, that we'll be looking at. First is electronegativity and the size of the A, or the Z. Here I used A, previous used Z. This is the atom in which the H is attached to. We'll see that. Electronegativity. Which is more acidic, H2O or HF? We need to look at the atom that the H is bonded to. Okay? And we need to consider the stability of the conjugate bases. Can you show a conjugate base for any acid? I'm not sure you can. You need to think about that and be able to do that. Very important to show conjugate bases. Conjugate base of water is that. Conjugate base of HF is this. The question is, which one of these is more stable? F minus is more stable. Why? Because it's more electronegative. The F nucleus likes being minus. It can thus handle being minus more. The more stable because it's more electronegative compared to oxygen. Everybody agree HF is more electronegative? That means it likes minus more. Because this is more stable, that means HF is more acidic than water. That means that this molecule is more willing to act as an acid and become F minus than this molecule is. Because this molecule becomes that when it acts as an acid, but that is not as good as that. And that's how we evaluate acid strengths. We need to look at conjugate phase of acid, which is more stable. Because that's where it's going. And the one that's going to a more stable place is the one that's more willing to do this reaction. Okay, please look ahead. So when we go through it on Monday, you will have seen it, and you'll be ready to ask questions and think in your mind, and et cetera, et cetera. Have a good day, guys.
Yeah, I remember. You gotta go take care of that thing before you go.
Wait, what? Like Charlie did the whole class? Charlie did like the whole
I wasn't going to all of them. I was going to the other one.
In this case, I Ron, you do a good job. It's also the first lab. For a few reasons, the most important thing is you ask if you seem to be concerned about doing a good job. Students who are concerned about doing a good job, usually they do it. Well, here. Oh, we got a name. Okay. I'll see. Wow, money. All right, we'll have some lunch today.
Have a good day.
It was there when you came in this morning?
I just saw it right now. I don't know what's going on.
Yeah, I don't think it's left.
Okay, I see.
Have you signed up for your move-in today?
Charles?
Oh, and then, no, I just want to
I'll give it to someone. Probably the main office upstairs, if you happen to see someone.
have a good weekend.
Okay, guys.